Chapter 5, Files, Directories, and the File System. Alrighty then. This week, we're getting into what I call the first of our real system administration subjects. Well, it is. I mean, up to now, we've been talking about hardware from a general point of view, about operating systems, the history of operating systems. It's all background knowledge, right? The stuff that it's good for us to know. But here in this week, we're getting into file systems and talking about specific things that we, as system administrators, do with the servers and the systems that we're responsible for. So what are we talking about? Well, we're going to talk about elements of the file system, what makes it up, both from the logical and physical viewpoint, right? Both are important and both are relevant. We'll look at how files are actually stored, what's actually happening on that little spinning magnetic piece of material. And we're going to look at how really the file system is laid out in both Windows and Unix/Linux, really, file systems. They are different. The principles remain the same, but the presentation is totally different. So we're going to look at that. And then we're just going to really briefly look at some of the command line commands for both Linux and the slide here says DOS. Really, it's the Windows command shell that's inspired by DOS. To move around a file system, some of our basic commands. So we're talking about file systems. And I don't care if this is a file system on a big multi-million-dollar EMC storage array all the way down to the little $3 thumb drive that's attached to your keyring that you put your homework on. We have file systems. And these file systems have certain things in common. The first thing we need to talk about is the concept of the partition. All right, great. What's a partition? A partition is really a form of storage virtualization. It is, well, the best way to illustrate this is a story, right? Let's go back in time, back to 1999, back when Bill Clinton was still president. And I remember I went out and I bought my first 1 gigabyte hard drive. And you're like, really, you bought a gig? Well, yeah, but back then, that was huge. I was upgrading from a 255 meg hard drive for my PC, my quote-unquote gaming PC, if you will. Well, I get that thing home and get it installed, and I'm like, you know what? I am never going to use all the space. What am I going to do with a gig of space? Well, what I ended up doing was partitioning it into more bite-sized 250 megabyte chunks. And let's look at what that really looks like. So let's say that this thing right here, this round thing, it looks like a bagel. I know. It's not. It is a hard drive. And it represents the platter. And here in the middle is a little spindle that the platter rotates around. Now, it's not really like this. This is just an illustration, but roll with me on it. It's cool. The partition represents the area of my disk that's usable, right? So what that means is I always have to have at least a single partition on any disk that I'm going to use. Well, if I wanted to, that's a 1, I could create just one big partition that encompasses the entire size of the disk. Sure, we do that very commonly nowadays, right? But I'm not limited to that. Because if I chose to, I could do something like this. I could put 2 partitions on the disk. Partition number 1, partition number 2. To the operating system that's reading this disk, it'll appear as though it's 2 separate hard disks. A C drive and a D drive, if you will. I can even do this. I can carve up to 4 partitions and present that to my system as 4 separate disk drives. My overall size is 1 gig. But each one of these partitions could be 250 meg in size. So the system thinks that it sees 4 250 megabyte drives. That's exactly what I did with that 1 gig drive I bought back in '99. Yep. On one partition, I installed Windows 98. On the second partition, I had like my gaming files. My third partition, I had like my schoolwork stuff. And on the fourth one, I put like bill paying and that kind of stuff on there. Separate it all right out. Keep in mind, this is a logical construct, and this is done using a tool like fdisk. Alrighty, well, within partitions, we actually format them with a file system. More to come on that later. And then within that file system, we have objects we can place in there. Well, there's one type of object called a directory, or a folder, if you'd rather. They're synonymous, 6 of one, half a dozen of the other. Directories and or folders are simply empty containers in which I can place other directories or folders or files. And within those directories, I can place other directories. And in those directories, I can place other directories. They can be nested. And in many cases, you'll see these go down 15, 20 layers deep. I mean, it can get pretty deep. That leaves us with files, which is really our most fundamental block or the component of a file system. Right? These are it's the meat and potatoes behind the whole thing. So it's why this all exists, right? Files. Well, files come in a variety of flavors. You know, you'd think I'd missed lunch or something. I mean, you keep making all these food references. Meat and potatoes, bite-sized, comes in different flavors. I really just went to Subway. I don't get it. Anywho, types of files. Fundamentally, we have plain text files. And these are files that simply have nothing in them but ASCII text. Remember our chapter on ASCII? Back there in numbering systems? Those. It's a file that contains only pure ASCII text characters. These are very common in Linux systems. On most of your configuration files that control how a Unix or a Linux system operates are plain text files. Let's contrast that to a binary file. Look at my examples here. A docx file. What's that? Well, you might recognize that. That's the type of file you save when you save a Word document. You're sitting there at school, you're diligently typing away your report, and you hit save, and it gets saved as, I don't know, report1.docx. Well, that docx is a file, a discrete entity, that contains the text you've typed in, but so much more. Right? This is a binary file, which means if I tried to crack it open in a text editor, like Notepad, like I can do with a plain text file, if I try that with a binary file, it's going to explode with a bunch of gibberish all over the screen. That's because those files not only contain what you've typed in, but it contains metadata. Data that describes and acts on the stuff that you typed into it. Look at a Word document, right? You can pick different fonts, different sizes, different indents, all kinds of these special effects type of things, right? Well, that has to be recorded in that file somehow, and it gets recorded with binary proprietary data to Word. So in order to open a binary file, you have to have the proper type of program. Word to open docx files, .xls or XLS files get opened by Excel, PPT files get opened by PowerPoint, and so on. You get the gist. File names. Nowadays, that's not such a big deal, right? Under modern versions of Windows, Windows 7 and up, your file name can be up to like 260 characters in length, including the entire path. I can have a file phrase if I want to. You know, all is fair in love and war .doc, if I truly want to. It wasn't always the case. Think back to when we talked about DOS and all the Windows operating systems that were based on DOS. They were limited to this numbering system right here, the 8.3 naming system. What that meant was I could have a file name up to 8 characters, a dot, and then a 3-letter file extension. Well, these are 4 letters. Why is that? Because modern systems aren't restricted to 8.3. But back in the day, it did. So that's why you used to see things like file1.doc, you know, spreadsheet1.xls. The whole purpose of the file extension Well, it's useful for us humans because we can look at that and go, oh, that's a Word document or that's an Excel document. But the OS does the same thing. File extensions tell the OS what program to use to open that file with. So if I'm sitting there in File Manager and I double click on the docx file, it's going to use Word to open it because of that file extension. If I double click on a .txt file, which stands for text, it would open it in Notepad, for example. Alrighty, pointers. Well, there's another word for that. It's called a shortcut, right? If you look at them right here, actually, this is the file that contains all the stuff for this course. And no, I'm not opening the exams for you. Sorry. These are all my different file names. Now, modern versions of Windows hide file names. Absolutely. But if I right-click on here, look at one of my choices. I can do a send to, where was it? Desktop. And it says create shortcut. Well, that's not actually sending that file onto my desktop. It's just sending a little icon that points back to the original file. Pointers are very common in OSs. They have different names in different OSs. They're known as symbolic links under Linux, but they all do kind of the same thing, right? They're basically icons or links that point to other files. They're not files in their own sense. All right, let's talk about compressed files. That's yet another type of them. We compress all the time. We just don't know it. And good reason to, isn't it? Let's talk about what compression actually is for a second. What's actually the data stored on disk, fundamentally? Really? Well, it's zeros and ones. Totally. So I got a series of zeros, 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 1, 1, 0, 0, 1, 1, 1, 1, 0. Right? That's my actual data on disk. Well, it's possible using, quite frankly, really hard math, using algorithms based on that, on mathematical constructs, to compress these binary strings into something smaller. So I could take this binary value I just represented here, or presented here, and represent it thisly. Where these 3 zeros get replaced by a single zero, 2 ones get replaced by a 1, 2 zeros get replaced by a 0, 4 ones get replaced by a 1, and so forth. Now instead of 12 bits, I'm representing this value in 5 bits. And again, the mechanism behind this is mathematical, and in many cases proprietary to your compression algorithm. But they all have the same effect. So I've effectively done is cut in half the size of this file, if that represented the entire file. Well, that's what compression is. That's exactly what compression is. So there's a couple types of them. We have one that's called lossless, which means the algorithm allows me to compress the file, but when I uncompress it, everything goes back to the way it's supposed to be. Right? I'm not losing anything. I could take a very high resolution picture, compress it, and then uncompress it, and I'm still high resolution. Well, that's one mechanism for it. What about lossy? What's that? These are compression mechanisms that basically throw out some of your data in order to get the file smaller. Right? JPEGs do this all the time. You take a file with your phone or your digital camera, and you save it as a JPEG. You're going to lose some of your information out of that file. The algorithm throws it away. But it does it in the interest of making the file smaller. Well, if you save a JPEG as a JPEG, it's going to throw some more values out and get fuzzier. And save it again and again and again and again, and eventually you won't be able to see your picture anymore because it'll throw out too much of the data. There's nothing wrong with that. It's just a different way of doing it. So compressed files, lossy versus lossless. All right, so let's take a look here. We keep talking about this file system, right? What is it really? Well, file systems are hierarchical in nature. More on that to come. I'm going to show you a pretty cool picture about that. And what they actually do is they map logical file names, file1.doc, to a physical location on that spinning disk. Right? If this represents the disk, This right here is a read-write arm, or excuse me, an actuator arm. There's a read-write head on the end of that, and this guy pivots, being driven by magnets. And what it does is it pivots over able to pivot over the entire radius of this disk. And the disk spins. Well, the disk is broken out into sectors. And data gets written in various sectors. Well, the file system is what keeps track of, hey, file1.doc is in sector blah, blah, blah. This one over here. Logically, we see partitions, directories, and files. Physically, though, this is what we're seeing. And it's usually not just a single disk platter, right? It's a whole stack of them stacked on top of each other with multiple read-write arms, read-write heads on multiple actuator arms. This is a spindle, and all the disks spin together. So file systems, what are they like? What are they called? What do they do? Which one should I pick? Well, it all depends on your operating system. Right, operating systems, file systems are very operating system dependent. If you're running Windows, a modern version of Windows, Windows 7, 8, or 10, you're using NTFS, which stands for the New Technology File System. Well, it's not that new. It was introduced back with Windows NT 3.51 back in 94, 95, but it's been updated. So NTFS is still our modern Windows file system. If I'm using a thumb drive, I probably have it formatted using FAT or FAT32. This is it's a very old file system. It stands for File Allocation Table that dates all the way back to the DOS days. And it's suitable for small little volumes. It can't read a very large volume, just by the way it's constructed. And it can handle things like security. Right? Because remember, original DOS was not a multi-user operating system, so there was no sense of users, there was no sense of security. Well, its file system didn't know it either. If you're running a proprietary Unix like Solaris, or maybe HPUX, you might be dealing with UFS. That stands for the Unix file system. Right? Like NTFS, it's been around for a while, and likewise, it's been updated over the years. If you're running Linux, you're probably using the ext4 file system. That's the current modern journaling file system that's included with most Linux distros nowadays. There's other ones out here there's more. Absolutely. I got ext3. I got ext2. I've got XFS. I've got ZFS. It stands for the zettabyte file system. It's designed to scale to, massive amounts of data. And so on. CDFS. There's many, many of them depending on your application. Now, one thing many file systems have in common is this concept of fragmentation. Well, let's look at that for a second. Let's take a look. What actually is fragmentation? If you remember back in the DOS years, we used to have to, or even the Windows XP days, we used to have a built-in disk defragmenter. We have to defragment our disk. Well, nowadays that's being done. It's done automatically. So it's kind of like, well, what's actually going on there? Well, here we are. So if this represents our disk platter, and again, it's broken out into sectors, or we could call it file system blocks in this case. Well, block size is not set physically. Block size, the size of each one of these little areas, is set by the file system, and it could vary. It could be 1K, it could be 8K, it could be 24K, whatever. Let's say that these are set to 8 kilobytes. Let's write that in there. Hey, there's 8 KB. And I'm going to save my report, report1.doc. Right? Well, I didn't get a whole lot done with it. So this file size of report 1 is only 4K. Well, what happens is the entire report is going to get written in basically a half a block. And then later on I go to save a game file for something and it fills in the rest of this block and into part of the next one. And then I go to save something else and that fills in over here. And save something else and it fills in over here. See where I'm going with this, right? But data changes. It gets erased. Things go away. So over time, my files are going to get spread out over my disk. What if I get a file that's more than 8K? Maybe I did a lot of work in my report, and now the file is 24K in size. So now that would incorporate 3 blocks. But stuff gets moved around on my disk, things happen, so pieces of it disappear and end up. I got part of my file over here. I got part of my file over here. I got part of my file over here. Well, that's bad. Remember that actuator arm? That thing that comes across here with the read-write head on the very end? And this thing spins back and forth? Well, that's spatial distance. It's actually got to move back and forth over my disk. Now, the space is only about an inch, maybe an inch and a half wide, and the disk has to rotate the correct sector underneath the read-write head. And it's spinning pretty fast, 5,400 RPM, 7,200 RPM for home systems. But it's still a very limiting factor. And if my file is spread all over the disk, then I'm having to read this sector, move the arm, wait for the disk to rotate, read that sector, move the arm, wait for the disk to rotate. What it makes my disk appear slow. And that's called fragmentation. Defragmenters cleared all that up. Defragmenters would go in, pretty much erase stuff, and then write it all right next to each other in contiguous disk blocks. Just like so. Now, my files, the data on my disk is right next to each other. That read-write arm doesn't have to bounce all over the place. It can just stay in one spot and read the blocks as the disk rotates underneath it. It makes for faster access. We may have seen something like this before. Remember this from the bad old days, the disk defragmenter? Right? Each one of these little blocks on here represented a block on your disk. And red ones were fragmented, blue ones were defragmented, and the bright blue ones here were not analyzed yet. Well, we still have defragmenters built in. Yes, we can still run them automatically, or we can still run them manually. Most of the time now they run automatically and we don't think much of it. But when we talk about fragmentation, that's what we're talking about. I promised you I'd show you what a Linux file system looks like, and here it is. Remember I said file systems are hierarchical? Well, what that means is everything comes to a point. And under Linux, everything comes under this one point here under slash. See that? Slash is referred to as root. No, it's not. I'm not talking about the lead guitarist from Guns N' Roses. I'm talking about that slash right there. This is the top or the root of the Linux file system. And every other folder in the file system is under root. And you can see it right here. That slash you see leading the file, this folder called bin, that represents the root file system. And again, folders can include other folders. So user here, USR folder, can hold other folders called bin, include, lib, and so on. Little out of scope for this class, but a key point under Linux is that everything in Linux is a file. Right? Users, devices, everything falls under this file system. If you're in the Linux command line, you need certain commands to be able to get things done. And here's just a rough example of them. ls to list the contents of directories. mv, the move command to move or rename files. cp to copy them. rm to delete files. cat, more or less, these display the contents of text files. mk directory, mkdir, I want to make a directory, I use that. rmdir, that's used to remove directories. But there's a catch about this. If you use rmdir, the directory must be empty. So you have to pre-empty it before you do that. Now, under modern Linuxes, there's easier ways of doing it. But this is just an example of what Linux commands look like. Contrast this for a minute to the Windows file system. Windows, like Linux, is also hierarchical. Absolutely. See this? But the one difference under Windows is it tends to be more drive-centric. Instead of having just slash over here, instead of having the lead guitarist from Guns N' Roses, now we've got C drive. So the drive itself, or the partition, remember I could take a physical disk and partition it, a C drive, a D drive, an E drive, and an F drive. That individual partition becomes the top of the file system. And anyone who knows Windows knows you can have multiple drives, C drive, D drive, so on. Like Linux, the Windows command line environment has commands to manipulate files within it. And they're very analogous to the Linux ones. So whereas Linux had ls to see the contents of a folder, under Windows it's dir, directory. Move versus mv, copy versus cp, del versus rm. Type, that if you type file 1, it'll tell you what kind of it'll throw the contents of it. It's like cat more or less under Linux. mkdir, rmdir, they work the same way. So the syntax is a little different, but what it's doing is the same thing, and the concepts are the same thing. So common tasks that we as IT people have to do with our file systems, well, we might have to set up disk quotas. Disk quotas are a way of keeping a single process or a single user from taking all your disk space. Right? Maybe you've allocated disk to your users. You've got 1 gig of disk space. A little small here. I don't feel like doing hard math. You've got 1 gig of disk space, and you've got 10 users. So every user should have about 100 megs worth of space. But you're probably going to have that one user that uses up 600 meg. Maybe he wants to bring in his or her pictures of their kids and throw them on your disk for you. Thank you very little. Great, you just used up all my disk space. Now my other users don't have any space, the ones that are actually making money for the company. Well, I can employ quotas. In that example, I could say, okay, every user out of this 1 gig volume, the most of each of these users gets is 100 meg. And it cuts them off at that point. They can't save beyond that. There's things known as hard quotas and soft quotas. Soft quotas are when you're feeling really nice, right? It's just a warning. Oh, by the way, your quota is 100 meg, but you've used 110. So, if you would delete some stuff, that'd be great. It's soft. It's polite. It doesn't enforce anything. Hard quotas cut you off, right? I mean, you're quoted to 100 meg, and you try to go past that. Bam, write failed. You need to remove something before you can save something else. They come in handy. Another thing we deal with sometimes is encryption. Right? The scrambling of that information, the encoding of it, to hide it from someone reading it. We most commonly do this on file systems for things like thumb drives or laptops when people are traveling. You don't want to be at the airport, and you've got your laptop with all your company proprietary secrets on it, and somebody steals it going through security. Well, that's a bummer. If it's not encrypted, somebody can just open it up, power it up, quite frankly, defeat the password function on Windows. It's not very hard, especially if you have the control of the box, and go in there and read all your files. Steal your ideas and make millions off from that should be yours. Or if you encrypted it without the decryption key, which is usually something the user has to provide, some type of certificate or maybe a password or a PIN or something like that, all they see is gibberish. It's encrypted. It's no good to them. So encryption is a way of protecting our data. A downside about this, though, it carries overhead. Right? It takes time to encrypt and decrypt things. So you have to have a good reason for doing it. Ultimately, though, we have file systems out there to share them. So our users can map them, which means attach their devices to it and write data and read data from it. It's the whole point behind it. This is the whole point behind file servers. And as IT people, we tend to maintain a lot of file servers, whether they be appliances or Windows machines or whatever. And look at that. That is a wrap. So this week we talked about file systems. Now this wasn't very in-depth. The later courses in the CMIT track will really go way more in-depth on all these concepts. But we introduced them. So it's all good stuff. So do the reading. Anything you're unsure about, definitely go in and review, and I'll see you on the flip side.